RoboHaptics, designing haptic interactions for lower body with quadruped robot dogs. RoboHaptics explores how quadruped robots can serve as non-wearable, lower body, reconfigurable haptic proxies, simulating impacts, obstacles, and everyday objects in XR. Since active and passive haptics have been used and discussed broadly in HCI domain, but only a few of them have focused on lower body and non-wearable configurations. In this study, we for the first time exploring the haptic interaction using a commercial robot dog. Based on the prior works, we have the following research questions. To summarize, we would like to ask, can quadruped robots safely and precisely deliver lower body haptics? RQ1, which lower limb locations can the robot reach across different postures? RQ2, how accurately does the robot's end effector, limb, align with predefined target points? RQ3, how precisely can the robot deliver repeated contacts under identical conditions? To address these questions, we outline a multifactorial design space for quadruped-mediated haptics. It captures posture, reachable body locations, robot parameters, and the types of haptic interactions they can deliver. Building on this design space, we developed the RoboHaptics toolkit, a library of motion primitives such as knocks, taps, presses, and pushes, each parameterized by force, duration, and intended use case.
Experiment 1 measured force output across 6 motion primitives and 3 postures. We used a calibrated load cell to understand the force inputs provided by the RoboDog. All remained below nociceptive thresholds. Experiment 2 systematically quantified the robot's reachability, accuracy, and precision across 3 stable postures: standing, sitting, lay down, using a life-sized mannequin. By placing the quadruped at fixed base positions and recording repeated paw contacts from 5 approach orientations, we mapped which lower limb regions were accessible and how reliably they were reached. Results showed sub-centimeter accuracy, with posture selection emerging as the dominant factor, governing both spatial access and the reliability of lower body haptics. Experiments 3 and 4 evaluated RoboHaptics with 12 participants. In VR, the quadruped simulated a coffee table, a garden fence, and a soccer ball, with participants rating immersion, realism, and comfort. Alignment of visual and tactile cues strongly boosted realism and immersion, while mismatches reduced believability. Outside VR, participants experienced 6 pre-programmed actions. They formed a tactile vocabulary: taps as notifications, presses as blocking, pushes as warnings, and gentle touches as reassurance. Taken together, these studies demonstrate that quadruped robots can not only deliver precise and safe lower body haptics, but also support a social language of tactile cues that extends the expressive potential of XR.
RoboHaptics, towards expressive lower body haptics with quadruped robot dogs.